My name is Brandon Burdett, and this is my Physics Lab 3 circuits. I'll get more into the details of the experiment later, but overall we were assigned with creating various circuits and recording various metrics including current and potential differences within these circuits. And the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, use multimeters or multimeters, however you're supposed to pronounce it, to measure the actual values of conventional current and potential differences in the circuits, and also to examine the behavior of ohmic resistors and capacitors. Here's a preview of the results of specifically the first circuit we created in this lab, and it pretty much just shows how the net voltage is going to be zero across the circuit. Now the system in this experiment is going to be the circuit, and the surroundings are everything else, which the main things affecting it are going to be like the desk and the air, which are in contact with the actual circuit itself. Now the two key principles in this lab are the loop rule on the left, which shows that the potential difference or the voltage is going to be overall zero, like we showed in the preview, and then the node rule is going to be that the net current is also going to be equal to zero, and that's called conservation of charge. Also, it's important to keep in mind Ohm's law, which is delta V equals IR, as this is an important relationship to know throughout the experiments within this lab. Now, for the first experiment we were tasked with doing, we had to create this circuit shown on the left with the two batteries, the ammeters, and the two resistors as well. And then predicting what the current's going to be is seen on the right as you find the voltage of the batteries, which are going to be 3 when they're added together, and then as well as the resistance of the resistors, which is 147 ohms. And then using that Ohm's law relationship we showed before, I is equal to V over R, and this will get us out to 0.02 amps. And in our actual experiment, I measured the current to be 0.096 amps, but we only used one battery, so multiply this by 2, and it's fairly consistent. Now the right is a visual of what our actual circuit looked like with all the wires and ammeter and batteries and resistors. And then on the left, we calculated the potential differences across each different thing, and they all added up to be 0. Now my group's numbers and the numbers needed for this graph are going to be slightly different because we only used one battery, but the overall gist has the voltage going down and then staying still as it goes from D to E, as this is kind of nothing, and then it goes down more, and then it flattens out at 0 towards the end. Now the second part of the experiment is to create this RC circuit, and I'm about to get into more details of what we actually do on the next slide. The procedure for this experiment is to create the RC circuit shown on the last slide with each bulb, and then measure the charge and discharge time using a stopwatch. So the components needed are the two bulbs, the battery, and the capacitor. And then after doing these experiments, the charge time comes out to be around 4 seconds, and this is how long it takes to get fully bright. And then the discharge time is around 40 seconds, which is how long it will discharge or become less bright. Now in this experiment there are a few areas for some error, which are like with my group we only used one battery for the first circuit, which is going to make our results a little bit different, and then also like different objects such as the desk touching the metal part of the circuit, which kind of can skew the results in a minuscule way. And then also our group didn't get to finish the lab in lab, so we also had to use online simulation for parts of the experiment, which makes our results kind of inconsistent, but overall the same. Now, if we were to have charged a capacitor with no resistor, then the ideal model would have had the capacitor reaching full charge almost instantaneously since there'd be no resistance. However, this would not be possible, and in real life, This would still be quicker, but it wouldn't be instantaneously, as there's still going to be a little bit of resistance within the circuit. Thank you for listening to my Lab 3 about circuits.